You use ChatGPT every day. You've probably asked it to write emails, debug code, explain complex concepts. But have you ever wondered how it actually works? How does a machine take your question and turn it into a coherent, intelligent answer? In the next 8 minutes, I'll break down the entire pipeline from start to finish, step by step. No math degree required. By the end, you'll understand exactly what happens between the moment you hit send and the moment that response starts streaming in. Let's start at the very beginning. Step 1. Tokenization. When you type a message, the model doesn't see words the way you do. It doesn't read English directly. It reads tokens. Tokens are the fundamental units that large language models work with, and they're not always complete words. Common words like the, hello, or code are each a single token. They appear so frequently that the model treats them as atomic units. But rare or complex words get split into smaller pieces called subwords. The word anthropomorphic might become 4 tokens: anthrop, omer, ph, ic. The word unhappiness becomes un and happiness. This splitting uses an algorithm called Byte Pair Encoding, or BPE. Here's how it works. You start with individual characters as tokens. Then you scan training data and find the most common adjacent pair. You merge that pair into a single new token. Repeat thousands of times. Frequent combinations like that become single tokens. Rare words get broken into commonly shared pieces. GPT-4 has a vocabulary of roughly 100,000 tokens. That's the total number of possible text pieces any input can be broken into. And when we talk about context windows, like 128K tokens, that's not 128,000 words. Tokens are shorter than words on average. The actual word count is roughly 75% of the token count, around 96,000 words. Why does this matter? Because the vocabulary size directly affects computation. Every token needs its own entry in the model's parameter table. Larger vocabulary means more efficient encoding, but more parameters to manage. Now, once we have tokens, we need to convert them into something the model can process mathematically. Step 2. Embeddings. Each token gets mapped to a vector. A vector is just a list of numbers. In GPT-4, each token becomes a list of 12,288 numbers. That's 12,288 dimensions. Think of each number as capturing one tiny facet of that token's meaning. The beautiful property of embeddings is that similar meanings end up close together in this mathematical space. The vectors for king and queen are close together. The vectors for king and banana are far apart. And you can do arithmetic with them. King minus man plus woman gives you a vector very close to queen. The model encodes semantic relationships as mathematical operations. But there's a problem. If you embed tokens independently, you lose word order. The dog bit the man, and the man bit the dog would look identical. So the model adds positional encoding. Each position in the sequence gets a unique signal added to its embedding. Now the model knows that position 5 is different from position 12, even if the token is the same. Now we arrive at the heart of the transformer. Step 3. The attention mechanism. This is the breakthrough that made modern language models possible. The question attention answers is, when predicting the next token, which other tokens should I pay attention to? Not all tokens are equally relevant. To predict what follows, the cat sat on the word cat matters enormously. The first, the barely matters at all. Here's how it works. Each token creates 3 things: a query, a key, and a value. Think of it like a search engine. The query says, what am I looking for? The key says, what do I contain? When a query matches well with the key, the corresponding value gets weighted heavily in the output. Every token computes attention scores against every other token. This is self-attention. The pronoun it can figure out what it refers to by attending to earlier nouns. The word bank determines whether it means finance or a river by attending to surrounding context like money or water. Now here's where it gets truly fascinating. GPT-4 doesn't run just one attention calculation. It runs 96 of them in parallel. These are called attention heads. Each head independently learns to detect different patterns. One head tracks grammar. Another tracks pronoun references. Another tracks semantic themes. Another focuses on positional relationships. All 96 heads operate simultaneously and their outputs get combined. It's like having 96 expert linguists each analyzing the same sentence from a different angle, then merging all their insights into one representation. There's a significant cost though. Because every token attends to every other token, computation scales quadratically. O of n squared. Double the context length, quadruple the computation. This is why long context windows are extremely expensive to run, and why there's active research into efficient attention alternatives. Step 4. Generation, also called decoding. After dozens of transformer layers have processed your input, the model produces a probability distribution over all 100,000 tokens in its vocabulary. If the context is the cat sat on the, maybe mat gets 12%, floor gets 8%, couch gets 6%, table gets 5%. The model doesn't pick deterministically. How it chooses is controlled by a few parameters. Temperature controls randomness. 0 means always pick the highest probability token. Deterministic, safe, but sometimes repetitive. Temperature of 1 means sample proportionally, allowing creativity and variety. Higher temperatures produce more surprising but less predictable output. Then there's top P sampling, also called nucleus sampling. Instead of considering all 100,000 tokens, you only consider the smallest set whose combined probability exceeds some threshold like 90%. This cuts off extremely unlikely tokens while still allowing meaningful variety. Generation is autoregressive. The model generates one token at a time, feeds it back as input, and generates the next. This is why generation feels slow. Each new token requires a full forward pass through the model. Modern systems use KV caching to speed this up. They store the key and value computations from previous tokens in memory, so each new token only computes against the cached values. Step 5. Training. Understanding this explains a lot about model behavior. Pre-training is the massive first phase. The model sees trillions of tokens of internet text. Its only job is predicting the next token. Given any text, what comes next? Do this billions of times, adjusting parameters with each prediction, and the model gradually learns language, facts, reasoning patterns, code, and more. After pre-training comes fine-tuning. Humans rate different responses for quality and helpfulness. The model adjusts using reinforcement learning from human feedback, or RLHF. This is why ChatGPT gives structured, helpful answers rather than random text completions. Training a frontier model costs over $100 million. Thousands of GPUs for months. And here's the key insight about hallucinations. The model is fundamentally a next token predictor. When it confidently states something false, that token sequence was simply probable based on training patterns. Probability does not equal truth. There's no fact-checking module. It just predicts what text should plausibly come next. Let's recap the full pipeline. Your text gets tokenized into subword pieces. Those pieces embed into 12,288 dimensional vectors. Positional encoding preserves word order. The attention mechanism lets every token understand its full context through 96 parallel heads. The output is a probability distribution over 100,000 tokens. One token is sampled, fed back in, and the process repeats. That's how every response from ChatGPT, Claude, or Gemini is generated. Billions of parameters performing this mathematical dance, millions of times per second, across thousands of GPUs worldwide. Next video, System Design. How Netflix serves 250 million users with near zero buffering. Subscribe so you don't miss it. I'll see you there.